Welcome back, pre-calculus students. We're going to take a look at a relationship now that exists within right triangle trigonometry. It's pretty special. You probably have recognized it. Maybe you've seen it in different ways, but you didn't even know it. What these are is we're going to label these points A, B, this line distance A, this line distance B, and the hypotenuse is C. Obviously, pretty familiar setup. What we're going to do is take a look at the relationship when we start with something like this, the sine of angle A. Sine of angle A will be the opposite A over the hypotenuse C. Then we're going to jump down to the other angle, the other acute angle, in this case angle B. We're going to say, what in the world is the cosine of angle B? The cosine of angle B is going to be the adjacent A over C. In other words, the sine of A equals the cosine of B. The reason why this is because when we look at triangles, opposite and adjacent sides are perspective. They come from whichever spot you're looking at. So when we go from A and we jump down to B, we're looking from a different angle. The opposite and the hypotenuse, the hypotenuse stays the same. The opposite and the adjacent flip-flop. These two are the same things. The sine of A and the cosine of B are asking for the same proportions, the same side ratios, but just the side perspective has changed. The angle's changed, so which two names you're using have changed. Well, these can be summarized in what are called the cofunction identities. The cofunction identities relate sine with its cofunction, cosine. So when we take a look at sine of theta, we need a way of talking about the cosine of, quote-unquote, the other angle. The other angle is the other acute angle that exists within a right triangle. So if we were to figure out, in this case, what would B be in terms of A? Well, you'd start with 180 degrees, which is all the degrees in a triangle. You'd subtract the right angle 90, and you would subtract the other angle A. So B would equal 180 minus 90 is 90 minus A. So this is angle B in terms of A. So when we say the sine of theta is equal to the cosine of the other angle, which is not what we write, what we're going to have to do is take 90 degrees and subtract theta from that. Obviously, if you wanted it in radians, by the way, it would be the cosine of pi over 2 minus theta. That's the same identity. I'm just working in degrees because we can get the basic ideas. Cosine of theta has got its cofunction is just sine. Those two relate. 90 minus theta. What's nice is tangent and cotangent remain paired up just like they would have been there with the reciprocals. So cotangent of tangent of theta will equal the cotangent of 90 degrees minus theta, and the cotangent will equal the tangent of 90 degrees minus theta. Cosecant is going to be secant of 90 degrees minus theta, and secant will be cosecant of 90 degrees minus theta. What's nice is if you're a visual person, this is played out in the graphs as well. So if we had a graph, and we'll just look at sine and cosine, where the sine curve looks something like that. The cosine curve starts up here, subtracts, gets a 0, and comes back up. The distance between any 2 points, in this case, let's say from -1 to -1, where are those values? Well, this is this 0 here is at pi. This is at 3 pi over 2. So the distance is pi over 2. Pi over 2? 90 degrees. In other words, if you start and you go back 90 degrees, you'll get to the same point. You'll get to the same peak, the same y values. That's just a visual way of saying, hey, that this idea, this cofunction identity exists. So what we're going to do now is take a look at how we can kind of solve some goofy-looking problems when we've been given weird angle measures, like secant of 75. And I'm going to change this right now. This should be the cosecant squared of 15 degrees. A couple things. Just in case you haven't seen this yet, the square root of cosecant squared, what that's really saying is the square root of 6 times the cosecant of 15 degrees squared. We put that squared right after the cosecant to indicate that that's what we're squaring. We're not squaring the 15. Now, let's focus in on this. The secant squared of 75 and the cosecant of 15 degrees. There's something really special here, and that's 75 degrees plus 15 degrees equals 90. That may not have jumped out at you, but as you get familiar with these are things you should be looking for, saying, hey, when do we have complementary angles? Maybe we can use my cofunction identities. What this means is that we can say the cosecant of 15 degrees equals the secant of 90 minus 75. That was poorly written. Let me write that over here, just a little bit more legible. Again, the cosecant of 15 degrees will equal the secant of 90 minus 75. This is really special. This is really important. Excuse me, 90 minus not 75, 15. The angle theta is equal to its cofunction of 90 minus that same angle. In other words, the cosecant of 15 equals the secant of 75. This helps because when I go to square the cosecant of 15, I can replace it with something I know. In this case, the secant of 75. In other words, I could take the square root of 6 times the secant of 75 squared, which is the square root of 6 times the square root of 6 plus the square root of 2 squared. That equals the square root of 6 times, when you square this, you get 6 plus the square root of 6 times the square root of 2 gives you the square root of 12 plus the square root of 2 squared gives me 2. We can keep simplifying this to say that equals the square root of 6 times 8 plus the square root of 12. And we can distribute to get 8 square roots of 6 plus the square root of 72. There's the perfect squares. We can simplify a little bit. 8 square roots of 6 plus, I think, a factor of 36 exists. So that's 6 square roots of 2. And there's our final solution.